Okay, we are continuing right along from where we left off in class yesterday. So if you remember, we introduced all these properties of algebra. I made you write them down in your notes, and then we went through this example together where we actually solved it out and then wrote down each reason why we could do each step. Okay, so now what we're going to do is we're just going to take some practice by looking at some steps, like one step, and just naming the property. So every time, here's how I think this should work. I'm going to go through them pretty quickly, all right? But what I want you to do is every time I show you a new one, I want you to pause the video and I want you to guess the property to yourself. And in fact, I even want you to write it down, okay? So right now in your notes for this one, I would want you to maybe write this down, draw a little arrow, and then write what property you think this would be. Once you have it written down, press play again. I will show you what the property is. And then if you got it wrong, you can pause the video again and correct it. But if you got it right, we can just move on. Okay, so every time I show you a new one, I want you to pause the video and try and figure out what the property is before you see me showing you the answer. Okay, so here's number one. Pause the video, try and guess, and then play when you're ready. So clearly from here, this side of the equation to this side, all we have done is distributed this 4 into the parentheses. So that would be the distributive property. Okay, and from now on, I'm not going to write property. I'm just going to write distributive or addition or whatever, but you get the idea. Okay, so if x equals 5, then 5 equals x. Okay. What property is this representing? Well, if we go back to our list of properties of algebra and we just look through, that's the property that is says that if we doesn't matter what order we write a quality. So that's the symmetric property. So if x equals 5, then 5 equals x. Those two statements mean the same thing. So this would be, as I just said, the symmetric property. Okay. So here's the next one, moving on. Okay. If, hang on, let me copy this real quick. All right, there we go. If x equals y and y equals z, then x equals z. What property is that? Well, once again, let's go back to our list here and let's look. What properties look like that? If x equals y and y equals z, then x equals z. Well, that, of course, is the transitive property, which says if one thing equals another and then that thing equals another, then, of course, these two things on the edge equal each other. Okay, so that's the transitive property. So we'll go back here. And it says the exact same thing, just uses different letters. If x equals y and y equals z, then x must equal z. That's the transitive property of algebra. Okay, let's keep going. How about this? If x equals y and x equals z, then y equals z. Is that the same thing? You'll notice that it actually is written slightly differently. Okay, so we're not actually using the transitive property here because it's not saying that x equals y and then y equals something else. What we're actually using is substitution. Okay, and here's why. If x equals y and then we're given that x also equals z, then what I'm doing essentially is I'm substituting in, because x equals y, and a y for an x in this statement. I'll try and say that again because that's kind of hard to see. Since x equals y, anywhere that I see an x, I can substitute in a y. So in this statement, if I substitute in a y for an x right here, what do I get? I get this statement. So this one right here is actually substitution, and that's pretty tricky. And to be honest, it doesn't really matter that you know the difference between substitution and the transitive property. So if you put the transitive property, you would not be counted incorrectly. But technically, number 3 is the cut and paste the transitive property, and this one is a little bit different. It is substitution. Let's keep moving on. Now, if x equals y and x equals z, then z equals y. That, once again, is the substitution property. Okay, that once again is substitution. It's the same thing, all right, except this time I'm substituting in a x for z. So in this statement here, because x equals z, anywhere I see an x, I can replace it with a z. So I'm taking this statement, I'm rewriting it here, but instead of x, I'm writing z, and that's how we get this statement. So that is substitution as well. Okay, let's move on. We got a few more. Here's what I want you to do. I want you to go ahead and do each of these and try to do all of them at once. So pause the video, write these down, and try and guess them, and then play the video when you're ready to see them, and we'll go through them really quickly. All right, so this one very clearly just says something equals itself, and if you go back and look at your page, you can see that is the reflexive property. All right. Here, if measure of angle A equals 30, then 30 equals the measure of angle A. That's the idea that it doesn't matter which order I write equality, so that's the symmetric property. For the next one, I'm going to write it down here. If the measure of angle A equals 30 and the measure of angle B equals 30, then the measure of angle A equals the measure of angle B. Now, look closely. Is that transitive or substitution? We have the measure of angle A equals 30, and the measure of angle B equals 30. Then the measure of A equals measure of angle B. Well, let's look at this statement. Here's the transitive property. Let's see if it's the same or different as this. This says if x equals y and y equals z, then x equals z. If this was the transitive property, then it should say something like this. Measure of angle A equals 30, and 30 equals the measure of angle B, then the measure of angle A equals measure of angle B. So since it does not, since it says measure of angle A equals 30 and measure of angle B equals 30, measure of angle A equals measure of angle B, that is the property of substitution. Once again, we're substituting in this statement, we're substituting in the measure of angle B for 30 since those two things are equivalent. Since those two things are equivalent. Okay? All right, and then lastly, we have if 2/3 x equals 12, then x equals 18. What did we do to go from here to here? Well, this 2/3 is connected to this x by multiplication. So in order to get x by itself, I would need to divide both sides by 2/3. And so that would be the division property of equality. Now, I also want to show you, however, that you could have used multiplication to do this, right? And some of you have learned to do this, and that's fine if you prefer to do it this way. Some of you know that, okay, if I want to get this x by itself, all I need to do is multiply it by the reciprocal of whatever fraction that is, and that'll end up being 1, and then I'll have x, and then I'll need to multiply this side times 3/2. And if you multiply 12 times 3/2, you get 18. So you could also use multiplication to do this. So I just wanted to point that out to you. This also could be the multiplication property. Now, why are we practicing all of this? Well, it is so that when it comes to proving math rules, we are able to be very familiar with these properties in order to prove some math truths. What do I mean by that? This is what I mean. Here is a proof, okay? And what we're going to do is, I want you to think of this proof as this is, here's our given information, and then down here, we know what we're trying to prove. And each of these statements and reasons is basically an if-then statement. This is, and if this is true, then this is true. And if this is true, then this is true. And if this is true, then this is true. So on and so forth, all the way down until we get to the point, the truth that we are trying to prove. And what we have to do along the way, though, is we can't just say, if this is true, then this is true. And if this is true, then this is true. And if this is true, then this is true. We actually have to go back and say why these things are true. We have to give reasons why. It's not good enough just to say if this, then this. We also must say why. So there's multiple ways to write proofs. This is called a two-column proof. Why is it called a two-column proof? Well, you can see here are our two columns. We have the statements, and we go down and argue our statements, and then we have our reasons. And so how we're going to introduce proofs to you is we're going to prove this using a 2-column proof first, and then we're going to go back and actually write what's called a paragraph proof using the exact same argument so that you can see both of these. Okay? So, go ahead and I would copy all of this, everything that's on this slide, down in your notes before we begin so that you can just watch and listen. You don't have to be writing as you're listening, and your brain can be focused on paying attention to what I'm saying instead of writing down. Okay? So, with all of that being said, let's begin your first proof. So, we always start with the information that is given. Now, our goal is to verify that AC and BD are the same thing. Okay? Our goal is to verify that AC and BD are the same thing. Now, what is AC and BD? I actually drew my picture wrong there. AC is this length right there, okay? And BD is this length right here. So our goal is, in this picture, to prove that those two lengths are exactly the same. Where do we even start? How are you supposed to even start this argument? Well, you always start by looking at the picture. This is our picture. Your first two statements, eventually you will have to write proofs where you're coming up with the statements on your own. But your first two, generally your first or second statement, always needs to be, sorry about that, I don't know why it just did that. Your first couple of statements will always need to be the given information. So look at this picture. Is there any information about this picture that is just given to us right off the bat? Your answer should be yes. We have these two tick marks. What do tick marks mean? Tick marks mean that those segments are congruent. So here, our first statement would be just what's given to us in the picture, and that's AB equals CD. We know that because it is given in the diagram. So we can say that this is true. This is because this is the given information. This is what we know already is true. Okay? Our next statement says BC equals BC. Well, that is quite obvious. Something equals itself. What's the property that allows us to say that? That's the reflexive property. Okay? That's the reflexive property. So, now that we have these two statements, what can we do with them? What can we do with these two statements? So basically what we're trying to do is combine these two and think, okay, if this is true, then what? And so you can see our next statement is AB plus BC must equal BC plus CD. Where is that coming from? How did we get from these two statements to that statement? What did we do? Stop the video and think about that for a second. How do we get from these two statements to these two statements? Well, you should notice that all we did was we took our original statement, AC plus AB equals CD, which we knew was true, and we used this to add the same thing to both sides of an equation. We took AB equals CD, and all we did was we added BC to both sides. Can we do that? Of course we can. Why? Because the addition property of equality says that if I take some statement and I add the same thing to both sides, that statement is still true. So this is completely valid. So if AB equals CD, and if BC equals BC, then I know that AB plus BC equals BC plus CD by the addition property of equality. That is how that works. All right? So, moving forward, where do we go from here? All right, so this is what we have so far. All right, and now what we either need to do is use this to make our next statement, or we need to introduce some new information so that we can eventually get to our point. And remember, it's always important to remember what the goal is here, where we're trying to go. And remember, where we're trying to go is to prove that AC equals BD. We want to prove that these two lengths are the same thing. Okay, so just as a reminder, midway through the proof. So now, here's the statement 4, and I want you to look at this. AC equals AB plus BC. Here's what this is saying. AC equals AB plus BC. Is that new information? Well, yes, kind of, because it's not based on any of these three statements. That's actually kind of a new statement. But is this also true? Yes, it is. Why is it true? Well, that by definition is the segment addition postulate. And I'm just going to write segment add post. Okay, that is the segment addition postulate. By definition, that if I add two smaller segments together, they make up a bigger segment. All right? And then this next statement is exactly the same thing. BD equals BC plus CD. BD equals BC plus CD, just with two different segments on the same picture. So that also is the segment addition postulate. Okay, and now you can see that we're at our last statement. Our last statement now says AC equals BD. So it's almost like a mystery. And these are all of your clues right here. And what we have to figure out is how we used all of these clues to get this statement. So remember, we used these two statements to get to this statement right here, right? So once we've used two statements to get to another statement, it's almost like we've used them up, they're out. Okay, and so now where we are is we have this statement, and then we introduce these two statements. So somehow we're combining these two statements in order to get this statement down here, and we have to figure out why. We have to use the clues to figure out how we put these together. Okay, well, if you look, we have this part of the statement right here, and I'm just going to clear all this out so that it's kind of easy to see. All right. Erase all this, and then I'm going to go back and I am going to cross out this part. We've already used those statements to come up with another statement, so we don't need to use them again. So if you look, AB plus BC, well, that is this side of that statement, right? And what we're saying is that AC equals AB plus BC. So anywhere I see an AB plus BC in an equation, I can substitute it in for AB plus BC. So on this side of the equation, I'm substituting in AC. And then you can see because BD equals BC plus CD, we can substitute in a BD anywhere we see a BC plus CD. So that's what I'm doing here. This side of this statement turns into just BD. So we actually took this statement right here, and on each side of this statement, because we were able to introduce these two truths, we substituted. We substituted in. We used substitution to substitute AC in for AB plus BC and BD in for BC plus CD, and that's how we got this. And so because we were able to do that mathematically and say why, we have a proof. We know for certain that AC equals BD. This is a truth. And a truth means that in any case, we're always able to use this rule now, since we have proven it, in any other instances. So anytime we have this instance, if we have this case, we also know for certain, because we've proven it once, that AC will equal BD. Because we've proven it in this case, this will be true in any cases like this. Anytime I have a segment that's broken up like this, and these two segments right here are equal, I can automatically know this segment will be equal to that segment. That's the power of proof. That's the power of proving that something is true. So this is your first proof. Now, there were probably some steps that I took here that didn't quite ring true with you or didn't quite make sense, and that is totally okay. That's totally normal. Writing proofs takes a lot of practice. It's a completely different frame of mind. So if you didn't quite follow along, no sweat. Don't freak out. There's no reason to freak out. These are hard, and they should be hard, and you will get better at them the more that you practice. Okay, so what we're going to do in class to start class on Friday is we're going to come back and we're going to prove this exact same proof, but instead of using a two-column proof, we will use a paragraph proof to do the same thing, just to show you a same form of the different argument. Okay, so I hope this wasn't too bad. Please come ask me if you have any questions, and then we will move on. Thanks.